Okay, hi guys. So we'll be continuing on seeing the calculation of n factor in case of disproportionation reaction. Let's start with the example. So suppose we have H2O2 or peroxide getting dissociated into water plus uh, let's say half moles of, I'm directly balancing the reaction, half moles of oxygen. So obviously in this case oxygen is going from -1 state to -2 state here. Example of reduction. Okay, and here oxygen is going from -1 state to 0 state, which is an example of rather this H2O2 is going from -1 to 0. This is an example of is it oxidation? Yes, this is oxidation. Why? Because H2O2 is releasing one electron to convert itself into a 0 state. Okay, so this is an example of disproportionation reaction. Okay, so here as you can see that the number of electrons used for oxidation would be, so there are two moles of oxygen converting from -1 to 0. Okay, so n vector for other number of electrons used for oxidation would be 2. Similarly for reduction it would also be 2, because uh, oxygen one oxygen atom from is going from -1 to -2 state, so two oxygen atoms would require 2 electrons. Hence for calculation of n factor we would be n1 times n2 divided by n1 plus n2. So this is 2 into 2 upon 2 plus 2, which is nothing but 1. Okay, so when H2 reacted with other reagents or other participates in reaction, we have this case that when H2O2 reacts with other reagents, then what will happen is we have H2O2 plus some reducing agent going to become H2O. So this is a perfect example of reduction in which oxygen is going from -1 state to -2 state. So here n factor for H2O2 would be taken as number of moles of H2O2 into number of moles of electrons required per mole of oxygen would be 1, so it would be 2. Okay, so if we take another example wherein we have again H2O2 reacting with some oxidizing agent and forming oxygen. So in this case again H2O2 is going from -1 to 0. Again the n factor would be 2. 2 into 1 would be the n factor. Okay, and we also know that molarity of H2O2 would be volume strength of H2O2 divided by 11.2. I hope you remember this from our previous lectures. And normality is nothing but molarity into n factor, and in this case molarity is volume strength upon 11.2 and n factor is 2, hence normality would be of H2O2 solution in either when it's used as a reducing agent or as an oxidizing agent, it would be volume strength of H2O2 divided by 5.6. Okay, this would be the answer. Okay, next we will be talking about the calculation of n factor in displacement or precipitation reaction. So let's get started with that. N factor in displacement oblique precipitation reaction. So first we have NaCl aqueous, which on reaction with AgNO3 aqueous forms AgCl plus NaNO3, again aqueous. So n factor here would be 1. Okay, let's see another example wherein 2 moles of AgNO3 aqueous reacts with BaCl2, again aqueous, to form 2 moles of AgCl as a precipitate plus BaNO3 whole twice. Okay, so here n factor for AgNO3 would be 1 and n factor for BaCl2 would be 2. Okay, and why is this the case? Because obviously this is in 2 moles and this is in 1 moles. Okay, and number of electrons consumed in the reaction would be, if we talk about this, number of electrons would be same in both the cases, and number of electrons is the n factor multiplied with number of moles, which is 2, and here number of electrons that should be used should be number of moles of, let's say, this compound, the n factor of this compound. This is, let me write it, NF2 and NF1 multiplied with number of moles, which is 1. Okay, so here we can put the value of n factor as 1 and here n factor value as 2. So the number of electrons exchanged or consumed or released in the reaction by one compound and the same number of electrons consumed released by the another compound should be same, hence n factor can be decided from the same or calculated from the same. We have K4 FeCN and what would be the number of Cn? So we are putting it at 6. Okay, plus 2 moles of FeCl2 undergoes Fe2, then we have another complex compound plus 4 moles of KCl. Rather, let's have 2K here or K2 here. Okay, so here if you look at the oxidation state of any of the atoms, iron is in +2 here. Okay, and also in +2 here. Similarly, it is in +2 here as well and +2 here as well. So you can't just decide here in the example of a displacement or a precipitation reaction by just looking at the oxidation state. So you have to just apply some logic like here, that 4 moles of K, this K is replaced by 2 moles of K in the product. Okay, so this implies that 2 moles of electrons were exchanged in the precipitate. So we know that the number of electrons upon the stoichiometric coefficient would be the n factor of this compound, hence n factor would be number of moles of electrons exchanged divided by stoichiometric coefficient, which is 1. So n is equals to 2. Okay, now let's say in general what actually happens, that A plus B, let's say, forms some compound here plus some compound here, and n factor for this is n1 and this is n2. So in the balancing of the reaction, what actually happens is we have balancing of this type, something like n2 times A plus n1 times B gives this compound plus this compound. This is the general thing which we observe. Why? Because obviously we discussed that number of electrons exchanged, consumed or released in the reaction should be equal for all the compounds, whether it is getting released from one compound and getting attached to another compound, so that's a different story, but number of electrons flowing from one compound and entering into the other compound would always be constant. So number of electrons that we can say that flows from A, number of electrons, we are just generalizing from A, let's say they are entering into B. Okay, so number of electrons from A would be n factor of A, which is n1, into stoichiometric coefficient of A. Okay, so stoichiometric coefficient of A, let's denote it by XA, and number of electrons entering B would be number, or the n factor of B multiplied by stoichiometric coefficient of B. So XA can be n2 and XB can be n1 via a simple gas, hence we just put it in a generality principle as a general rule. Okay, let's see another example on the same. Suppose we have S2C2O4 combining with 2 moles of NaOH and forming Na2C2O4 plus 2 moles of H2O. Okay, so in this case no compound in this case, or no atom in this case is changing its oxidation state. Okay, so this is also example of displacement or a precipitation reaction. So in this case we know that 2 moles of H2 were actually replaced by 2 moles of Na2, hence n factor would be 2 here, and n factor here would be again 2 moles of electron were exchanged divided by 2, which is the stoichiometric coefficient, which is 1. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing more examples on calculation of n factor in case of displacement and precipitation reaction.